In this video, we're going to look at a new reaction of haloalkanes called the Grignard reaction. This is one of the most, this is a very powerful reaction, I'll just say that. It's very powerful, it's very interesting. If I had to be honest, this is the reaction that when I was in Organic Chemistry 1 and I learned about this reaction, I really got excited about organic chemistry and the types of molecules that could be made. So without further ado, this is called the Grignard reaction. It's named for Otto von Grignard, won a Nobel Prize for this in the early 1900s. But those details aside, let's focus on the things we need to know. This is typically a reaction that we would do in lab. It's a little bit involved and things can go wrong, so it doesn't make sense to do this when we have a limited timeline. But suffice it to say, it's a very useful and important reaction. And this allows us to convert haloalkanes into alcohols. This is our first kind of the first kind of experience with alcohols, I guess. So I'll just define these as ROH. In upcoming lectures, we'll actually look at what the look at the chemistry of alcohols and that sort of thing. So we're going to convert haloalkanes into alcohols. So let's just remind ourselves that alcohols have this ROH. They're also called hydroxyl or hydroxy alkanes. Hydroxy is an interesting term, but it's just referring to a substituent that is an OH group. So an OH group as a substituent. So an example, and this is a normal lab experiment, one that we could have done with more time and I guess fewer viruses. Anyway, what we do is in the lab, we would take 1-bromobutane and react it with acetone. You might recall from the IR lab that acetone is a ketone or a carbonyl. And what I want us to focus on is that we have a carbonyl present. And the carbonyl is the carbon-oxygen double-bonded species. And over the arrow, we're going to put magnesium, and I'm going to put a little 0 as though it's a degree, but that's just implying magnesium in the 0 oxidation state, and we'll look at that along with this, which is our solvent molecule. And the outcome for the reaction is right here. Okay, so kind of a complicated product. If we count up some carbons, we can see maybe where stuff comes from. You can't create or destroy matter, but if I count up the carbon atoms on the left side of the chemical reaction, I see that there are 7 carbons. And if I count up the carbons in the product, I see that there are 7 carbons and then 1 oxygen. And that 1 oxygen comes from the carbonyl. So this is an interesting reaction because we take 2 readily available starting materials, haloalkanes, which we've just done a lot of, 2 readily available starting materials, and we generate a very useful functional group, which is the alcohol. So let's break this down, and that's what we'll spend the next couple of lectures looking at. So the starting materials are, again, number 1, the haloalkane, which is Rx, some sort of, and in this case, it's Rx, but in this case, it is 1-bromobutane. The other starting material is the carbonyl, which again is a ketone or aldehyde in most cases. And the carbonyl really is just some functional group with a carbon double bonded to an oxygen. Ketones and aldehydes are most common for the Grignard reaction. You're not going to see too many of the other types of carbonyls like esters and amides and that sort of things for some reasons we could talk about in organic chemistry too. So we have our starting materials. Now let's look at the other conditions. So the reagent is magnesium and then superscript 0. This is magnesium in the 0 oxidation state. And when I see 0 oxidation state for a metal, what I'm noting is that this is metallic magnesium. Metallic magnesium. So when you handle this, it actually looks like a metal as opposed to a salt. Salts would have some sort of negative counterion attached to the metal by way of ionic bonding, and we would have had a redox process occur to convert the magnesium 0 into some magnesium with probably a +2 oxidation state. So, and we'll look at that later, but magnesium and other oxidation states. But the next thing we want to include is the solvent. So the solvent is typically diethyl ether. And so if we look, anytime you have an ROR functional group, that is an oxygen with 2 non-hydrogen, usually, I mean, 2 carbon things attached to it, no hydrogens. This is called an ether, has an interesting history. And then this is an ether with 2 ethyl groups. And hence it's called diethyl ether. Okay, where again, if we see ether, we think this. All right, so that's the solvent. Now, what we really need is for the solvent must be a protic and have an oxygen that is sp3. So we usually just use most ethers. And ethers work well, and of all of the ethers, diethyl ether is the easiest one to get our hands on. Okay. So what we've done is we've kind of broken down the conditions. We looked at one example, but we're still far away from being able to predict the products and propose a mechanism. What I like to do is try to show you the mechanism before I start having you predict the products, which can be backwards in some cases, but it's just really the way to look at this. So the first thing to recognize is we need to learn some additional chemistry before we can see how this reaction works. So how does the Grignard reaction work? How does this work? So if we know how it works, we can predict products, propose mechanisms, and that sort of thing. And what we need to notice is how it starts. It starts with magnesium 0 reacting with our haloalkane. Now what we're going to see is that if we have some Rx group and that sees magnesium 0, okay, they're going to spontaneously react with each other to make an interesting product where the magnesium is now directly bonded to the R group or the carbon atom. On the next page, we'll look at this in the context of the example that we would typically do in the class for the lab. Okay, so the magnesium actually jumps in between the R and the X group. Now, in class, what that would look like is we would take 1-bromobutane and react it with magnesium 0 to put the magnesium between the carbon and the bromine atom. Now, this has a special name. This is called the Grignard reagent. And it stems, it could be more generally described as RMG attached to halogen. What we want to notice about this reaction is that magnesium 0 goes from the 0 oxidation state to the +2 oxidation state. So this is a process that's used a lot in chemistry. It's called oxidative addition. The magnesium is added and been oxidized simultaneously. It went from a 0 oxidation state to a +2 oxidation state. Said another way, with the +2 oxidation state, that means that we're now magnesium 2+, or I never really, I don't worry too much about it. I was told to put 2+ or something, but whatever. You can write magnesium +2 or 2+, and this is after the Grignard reagent forms. Okay, so that's what's happening to the magnesium. It forms a salt. Now, what's a salt? A salt is some positive metal with negative counter ions. Now, I'm trying to simplify this a little bit. So salt is a metal with negative counter ions, like sodium metal with a chlorine counter ion, that's table salt. Typically, magnesium would form ionic bonds with like 2 halogen atoms. So we would have magnesium and 2 Br atoms, and that would form MgBr2, which is a salt. What we could also have now, and what I'm getting at is magnesium likes to, let me say it this way. Magnesium likes to be bonded to needs 2 -1 groups bonded to it, and that should make sense because it is in the +2 oxidation state. So if it's going to be neutralized, it's going to have 2 -1 charged things attached to it to neutralize its charge. Well, what if one of those things is carbon? If one group attached to Mg 2+ is carbon, the carbon is anionic. And that's kind of the key takeaway about the Grignard reagent, is that in the case of the Grignard reagent, the carbon is now sort of negatively charged, like an anion. So if we look at that, that starts to make sense because, well, and I'm going to draw it over here for hopefully you can see in a second good reason. What I'm getting at is that this magnesium 0 is +2, and it's countered by a Br, which is -1. Well, that's no big deal. Br is -1. It's just not a big deal, right? I mean, like, halogens with a -1 charge. We see those all the time with salts, with leaving groups, that sort of thing. But over here at this carbon atom is also -1 charged because it's attached to a metal now. That's really cool. Please appreciate how cool that is. Why is it so cool that it's negatively charged? Well, before the reaction occurred, we had this molecule, and before it reacted with our magnesium 0, we had a delta plus on the carbon atom and a delta minus on the bromine atom. The bromine doesn't really change, but in the presence of the magnesium, the carbon flips from being delta plus to almost fully negative. Now, I'm being careful about my words, and maybe I shouldn't be. You could think of that carbon, this carbon right here, as being completely negative. The reason why is because it's bound directly to a metal. That's super interesting. Now, the reason why I'm being careful is because when carbon's bonded to magnesium, there is some covalent bond character, and so I wouldn't be totally correct calling it a full-blown negative charge. But it behaves like one, especially in our context. It's going to behave like a full-blown R with a negative charge. That is to say that in the Grignard reagent, this behaves like carbon with a negative charge, or more generally, R minus. Now that's the big takeaway, is that Grignard reagents allow us to make, and by make, I mean easily make, very easy reaction to do, easily make. I mean, things can go wrong, it takes time, you know, it's not one of these things we can do in like a half an hour, that sort of thing, but it's pretty easy to make R negative / these are also called carbanions. And they're not full-blown carbanions. They're called carbanion equivalents because they behave like carbanions without being them. But you, as an introductory organic chemistry student, can think of them as R minus and go very far with a full-blown carbon with a negative charge. This is significant because up to now, there is no good way to make R minus. Carbon attached to hydrogen is not acidic. So having a base around it'd have to be a very strong base, definitely like not hydroxide or something. Even some of the stronger bases like the E2 bases couldn't pull it off, having us deprotonate CH bonds. So we have to make them by a different way. Well, why don't we just make them with haloalkanes, these things that are actually fairly easy to come by with metallic magnesium, and magnesium is the opposite of a scarce metal. These are wonderful conditions for generating carbon anions. They use haloalkanes, which are easy to come by, along with metallic magnesium, which, while it's hyperreactive, it also is easy to come by and easy to get. So these are really impressive conditions. Now, can we use them to do something useful? Definitely. So the key thing about the Grignard reaction is that once you form the Grignard reagent, in the Grignard reaction, the R minus, I guess I could write that up here. I'm always limited on space. The R minus will add to the carbonyl to make a C-C bond. That is a big deal to us. We've only seen a few very specialized examples of making carbon-carbon bonds. But as you can probably guess, if you want to make a very complicated molecule and generate something, if you want to generate a huge number of things that could potentially do interesting things, making carbon-carbon bonds is the way to go, right? I mean, the more sophisticated the carbon-carbon bonds are, the more diverse the structures can be. The more diverse the structures can be, the more diverse their functions can be. So we make a carbon-carbon bond by adding to a carbonyl. So I'm going to draw the R minus, and this is from our Grignard reagent. and we're going to add it to the carbonyl. Now what I'm going to do is I'm going to draw the carbonyl up here. Just give me a second. I'm going to leave a little bit of space. And really, it's because I can draw the carbonyl in two ways. Now, the second way is a little bizarre, but it takes into account something called resonance. And we'll get to resonance here in a second. But the R minus, the negative charge on our Grignard reagent, is going to add to the carbonyl carbon and push the electrons up and onto the oxygen. Recall that there's a difference in electronegativity between carbon and oxygen, so any covalent bonds are going to be polarized and distorted so that the electron density is more on the oxygen atom. So it's pulling the electrons away, and you can think about there being a delta positive, or what you can do with double bonds, which is kind of interesting, is you can actually push the charge, one of the electrons between the two atoms, onto an atom. We'll look at that on the next page. Anyway, the R minus is attracted to the carbon atom, and we adds to that carbon atom, and it pushes the electrons up. Let me trace those arrows just so you can see what I'm talking about. We're going to take one curly arrow. The negatively charged thing does the attacking, and it's going to attack the carbon. And then so as to not break its octet, the carbon is going to boost its electrons up and onto the carbonyl, and that's going to give us this species where we retain our balance of charge. We were overall -1 on the left, and now we're overall -1 on the right. But on the right side, the oxygen atom now has the negative charge. If you look, the new bond is positioned here. It's between the R group and the carbonyl carbon, where I could kind of go like this, just to give you a sense of where everything is. Now, if we have a charge-separated species, maybe you can see it even easier. The negative is attracted to the positive. Here we don't have to push the electrons up. They're already up, and that would actually give us the exact same structure. So that's a way to show it with one arrow. But maybe you don't understand why I would draw the charge-separated species, and we'll look at that later. Okay. So we've attacked the carbonyl carbon. Let's do that. Let's kind of make note of that. So the Grignard, the R group on the Grignard reagent attacks the carbonyl carbon, and it's always the carbonyl carbon. And this is going to be our carbon that's right here. Or I said we could also draw a charge-separated species, which is right here. Now what that forms is this forms an alkoxide. Alkoxides are like alcohols, but they've been deprotonated, or they've lost hydrogen. So an alkoxide is a deprotonated alcohol. That is to say, if we have ROH, which is an alcohol, and we react that with some base, we form an RO minus. And that's an alkoxide. That nomenclature is similar to hydroxide. If we have H2O, which is water, we could form HO minus after reacting with a base, and this is hydroxide. So alkoxides are hydroxide versions of hydroxide versions of alcohols. Okay, they've lost the hydrogen by an acid-base reaction to give an O minus. The O minus is the key. The O minus is kind of, I guess I'll write that, it's a bit awkward. The O minus is the key to an alkoxide. It's just something with an O minus attached to an R group. So we form that as a result of the Grignard reaction. So we have R minus from our Grignard reagent adding to a carbonyl to make an alkoxide. Okay. So we have this alkoxide, and then what happens to the alkoxide is we introduce sort of a third stage. This third stage is called the quench or workup. So quench means to kind of get rid of. Like if you quench your thirst because you drank Gatorade, your thirst is gone. So this is called a quench. For a reaction quench, we are going to kill the reaction. This is also called workup. I don't really know where the term workup comes from. I mean, it's just one of these things you hear people kind of throw around, but workup means to kind of finish up and polish off whatever you're working on. So you finish working it up, I guess, just kind of an awkward phrase. But you're going to work it up with H+, which is acid. It's usually dilute acid. And it's usually dilute HCl. Now what this will do is neutralize the alkoxide to form the alcohol product. Now what that looks like is, if we look at our example from up above, we would have RO- reacting with H+ from the quenching solution, from our dilute HCl that we add to the reaction mixture. Negative combines with positive to give us a neutral alcohol. It's kind of our neutralization agent. In stage 3, all we're doing is cleaning up and killing the reaction, because otherwise we would have a bunch of alkoxides as salts, which are harder to deal with than alcohols. Okay, so we have 3 stages, but I didn't really fully define the first 2 stages. I mean, we talked about them. We did in detail. If you're following along, they should be, once I bring them up, they should be fairly clear. But let's go ahead and kind of list these again. So in step 1, and let's actually title this Stages of the Grignard Reaction. In stage 1, what we have is formation of the Grignard reagent. In this stage, our haloalkane reacts with magnesium 0 to form the Grignard reagent. We call the overall process oxidative addition because the magnesium squeezes in and adds between the carbon and the bromine, and when it starts as a 0 oxidation state species, it finishes as a +2 oxidation state species. So it adds and it gets oxidized. So this is now our Grignard reagent, which is equivalent to R-. But if we had, when we started with Rx, we added it to Mg0, and then we got RMGX, and again, that's equivalent to R-. In step 2, we add the carbonyl reactant. We usually don't have the carbonyl reactant present at the outset of the reaction when we're forming the Grignard reagent. We kind of add the magnesium and the haloalkane, let them stir and mix and form the Grignard reagent. They form a nice cloudy solution. And then we add the carbonyl reagent. We add the carbonyl reagent so the Grignard reagent can add to the carbonyl carbon. I know that's kind of cumbersome wording, but I think it's helpful. So the Grignard reagent can add to the carbonyl carbon. Okay, so what that looks like is that we have R- adding to the carbonyl carbon, and that's that carbon that's double bonded to the oxygen. The arrows for that are negative, adding to the carbon and pushing the electrons up and onto the electronegative oxygen atom. That forms then an alkoxide salt. And the carbonyl, let me just be clear, could be anything. Acetone's a nice starter thing. I like to use acetone instead of something with a bunch of R groups, though I could. and it could be an aldehyde. Now, as I mentioned, and I'll probably have to go over in the next lecture, it seems like a bit to include over here, but we could also draw a charge-separated version of the carbonyl. These two are actually the same structure. Okay, we've just drawn the double bond differently. We'll get to that next lecture. Anyway, when you draw the charge-separated species, it's a little bit easier to see the combination of the minus to the plus, and you don't have to draw a second arrow with your mechanism. That will also give you the alkoxide salt. And then in stage 3, we neutralize the alkoxide salt with H plus to quench / work up the reaction. So what that looks like is we take our group is already added to the carbonyl, so we now have our alkoxide. We add our H plus, negative adds to positive. We're overall neutral on the left side with both a negative and positive ion. And we don't have an ion on the right side. We just have our neutralized alcohol. Okay, so these are the 3 stages of the Grignard reaction. It's pretty much a mechanism at this point. I can't provide any more curly arrows, really. Stages 2 and 3 have curly arrows. Stage 1, it's a little tedious, not tedious. It's beyond the scope of this class to draw the curly arrows for the oxidative addition to form the Grignard reagent. Okay, so I think that's a good stopping place. In our next video, we'll look at why I can draw a charge-separated carbonyl with the negative and the positive on the same molecule.